Moving on to aqueous ionic equilibrium, we're going to be learning more stuff that's related to the acids and bases that we covered in chapter 17. We've got a quote to open us up. In the strictly scientific sense of the word, insolubility does not exist, and even those substances characterized by the most obstinate resistance to the solvent action of water may be properly designated as extraordinarily difficult of solution, not as insoluble. So basically the takeaway from this quote, or what Otto is saying here, everything dissolves. It just maybe doesn't dissolve very much at all. Like, it might be difficult even to measure how little it dissolves. You may know that dogs and cats die from eating, ingesting, drinking antifreeze. And that's because ethylene glycol, which is one of the common active ingredients of antifreeze, has a sweet taste. It is also an alcohol. It's got these OH groups on the ends that make it an alcohol. And so the initial symptoms of drinking ethylene glycol, don't recommend it, resemble drunkenness because of that alcohol action. However, unlike ethanol, that's the one that you can drink relatively safely. Ethylene glycol is metabolized to glycolic acid, which the skincare minded of you may recognize. And that enters the bloodstream and drops the acidity of blood, which is very bad. That's the death part of ingesting ethylene glycol. Blood pH is really important because a lot of our proteins have developed to function in the pH range of our blood. And for our blood, that's a pretty narrow range, 7.36 to 7.42. So you can imagine just a little change taking you out of that range, or a big change, like if you drop that below 7, that's going to cause some real big damage really fast. Like lots of biological processes probably shutting down from that change in pH. And the reason that our blood can stay in that very narrow range is because of buffers. You may remember buffers from Chem 3A, hopefully Chem 3A. It should have been talked about at least a little bit. So what is a buffer? A buffer is a chemical system that resists pH changes. Buffers resist pH changes. They can neutralize both added acid and added base. So they don't just stop acid, they don't just stop base, they actually can stop both. And the way that our blood buffer works, press the wrong button, our blood buffer is a mixture of carbonic acid, like the stuff that's in carbonated drinks, and the bicarbonate ion, like in baking soda. So we've got carbonic acid, that's our first line of equation here. Carbonic acid can react with added hydroxide to form bicarbonate ion and water. And the bicarbonate ion that's also present in the bloodstream at the same time can react with protons or hydronium ions to reform that carbonic acid. So both of them are in there at the same time. If you get large enough amounts of glycolic acid in your blood, that's going to overload the capacity of the carbonic acid, and then you will start to build up excess H+. So once HCO3- is depleted, H+ can change rapidly. If you think about the titrations that we've done in lab, especially the ones that took a little bit of time to get ramped up, as we were adding in base, you saw the pH just kind of slowly rise, just very slowly, and then you reach the equivalence point. That's where we're overwhelming the amount of acid, and then our pH spikes. That's sort of what we're talking about here. So once we're doing the opposite here. So once our base, in this case, is overwhelmed, then our pH is going to start to plummet because there's nothing to negate its acidic capabilities. Low pH in your blood results in acidosis. It's even got acid in there, so you know that it's low pH. And that affects the equilibrium between your hemoglobin and your oxygen. So hemoglobin and oxygen, there's an H plus that's swapped in there. And so if you overload the H plus side of this, then we're going to cause a big shift. Thank you, Le Chatelier's principle. We're going to shift our equilibrium to the left, and we are going to force all of our hemoglobin, or lots of our hemoglobin, to unpair with oxygen. And that's incredibly problematic because then that oxygen is not going to be able to get around to the rest of your body, your brain, your muscles, etc. And so then you basically, suffocate. Or that's what I would imagine. One treatment for things like ethylene glycol, I think you can do it for, it's either methanol or isopropanol, rubbing alcohol or wood grain alcohol, not respectively. One treatment for that is the administration of ethanol. So if you, for some reason, know somebody who's like, hey, they're drinking antifreeze, give them a couple shots and then drive to the hospital, drive to the emergency room as fast as you can. And the ethanol, here it says, is preferentially metabolized. I think for methanol and for isopropanol, it's a competitive, non-competitive, or a-competitive. It's one of those three. But the long and short of it is that the ethanol gets processed and some of the methanol and isopropanol gets processed a little bit more slowly. So it just slows down and buys you time. In case you're wondering, high pH in the blood is alkalosis. I was wondering, so I looked it up so that I could tell you, because I thought maybe you would also want to know. Anyway, so I think that this won't show up on a test or anything, but the treatment with ethanol, I think that's a good thing to keep in mind, because usually there's some ethanol somewhere in the house. Even if you're a teetotaler, it might be in, some cooking wine or something. Okay, getting on to more important things. Buffers. So as we talked about with the example being our labs, the pH of solutions can significantly change if you add acid or base. Buffers magically resist pH change. And the way that buffers do that is they contain significant amounts, maybe even similar amounts, of a weak acid and its conjugate base, or a weak base and its conjugate acid. So we can swap those two terms. So a buffer system has weak acid and the conjugate base, both sides of the equilibrium equation, or weak base and a conjugate acid. Those are two options for buffers. Notice that we cannot form a buffer with a strong acid or a strong base. So those are your critical definitions for buffers. You definitely will want to know those. So for making a buffer, we are going to have possibly a weak acid, so something like acetic acid in vinegar. We're going to add some weak acid to our buffer solution pool. Just adding the weak acid isn't enough. The extent to which acetic acid or any other weak acid is going to ionize or form H plus in solution is not significant enough for us to form a buffer solution. So we would also need to add in the conjugate base. And in this case, we're doing that by adding sodium acetate. So acetate is our conjugate base. So adding both of those things together so that we have both the weak acid and the conjugate base in significant amounts in our solution. Questions about buffers? All right, which of these solutions is a buffer? All right, coming back, what do we think, which of these solutions is a buffer?
D.
We've got a guess for D. Why do we think D is a buffer solution?
Because A has a strong acid, I think. Or C, I just went with the NaCl. I thought it is a weak acid, I think. Or it's a strong. I just went because it's a nitrite instead of a nitrate.
Because it's nitrite instead of nitrate. Okay, well, let's look through our options. So starting with A, we've got HNO2, nitrous acid. That is a weak acid. Great. So we've got one of our two components that we need for a buffer. We also need to see, show me a conjugate base. But instead of a conjugate base, we have a strong acid, HCl. Okay, so that does not meet our definition for a buffer. In B, we have nitric acid, HNO3. Nitric acid is a strong acid, and so we've already struck out there. We do, however, have its conjugate base, but that doesn't matter because it's a strong acid. And we know that, so part of the reason that it's weak acid and its conjugate base is that the conjugate base for a strong acid we know is pH neutral, whereas the conjugate base for a weak acid is going to affect the pH of the solution. It has pH potential. All right, for C, we've got a solution with HNO2. That's a weak acid. And we have NaCl, which is not the conjugate base. That's just a salt. So we're missing the conjugate base part for C. D, as correctly identified, is a weak acid and the conjugate base. We also have our counter ion sodium just to keep that charge neutral. So our correct answer here is D. Because we're in Chem 1b, we can calculate the pH of a buffer solution. So let's consider a solution that initially contains 0.100 molar acetic acid and the same concentration of sodium acetate, its conjugate base. So we've got 0.100 molar of the weak acid and the conjugate base. So both of these sides we have a significant amount, at least of the stuff we care about. The presence of our acetate ion, the C2H3O2 minus, causes our acetic acid to ionize less than it normally would because we've got a significant presence on the product side. So normally we would just see a shift from left to right because we don't have anything on the right side. Since we've buffed up the right side, that's going to reduce the amount. It's sort of a Le Chatelier's principle sort of thing. So instead of all pushing to the right, we've got a little bit more of an even fight. And so our acetic acid is not going to ionize as much. This is also known as the common ion effect. So swap out acetate and acetic acid for any other set of things that have the same. All right, let's calculate the pH of a buffer solution. That is these concentrations. So we've got acetic acid and sodium acetate. We've got a Ka value. It'll be helpful for us to have an equilibrium reaction expression. So we've got acetic acid is going to be in equilibrium with H plus and C2H3O2 minus. I'm omitting some of the other stuff that we don't really care about, like there's a water in there, sure. We're just going to represent H plus instead of hydronium. And yes, there's a sodium in there, but we don't really care about the sodium part of it. And the concentration of our acetate is going to be the same as the concentration of our sodium acetate. So we can do our favorite, it's an ice table. One of these days we'll get away from ice tables, I think, but today is not that day. Some of you may be starting to see why I had a visceral reaction when I saw ice tables after over a decade of not using an ice table. Okay, so we've got our initial concentrations given to us. So for HA, that's our acetic acid, 0.200 molar. Initially, we have no H plus. And for our A minus, that's our acetate ion, got 0.100 molar. Which direction is our equilibrium going to move initially? Is it going to move left to right or right to left? It's going to be left to right. We don't have any H plus, and so we can't move in the left direction. Same as with all our ice tables for acids before. So it's still our minus x plus x plus x, but it's helpful to remind ourselves that we're thinking about Le Chatelier's principle here a little bit, or at least some of those concepts. And so then our equilibrium concentrations, we'll add those together. For H plus, it's just x. And it's 0.200 minus x and 0.100 molar plus x for our acetate. We can then write our acid dissociation constant expression, our Ka constant expression. It's our concentration of H plus times the concentration of C2H3O2 minus over concentration of acetic acid. How are we doing so far? Great. All right, so then we can plug in some numbers and some x's. So we're going to have 1.8 times 10 to the minus 5 for our Ka. Our H plus at equilibrium is going to be x. Our C2H3O2 minus 0.100 molar plus x. And our acetate, our acetic acid 0.200 minus x. If we take a look at our Ka value, it's 10 to the minus 5, and our concentrations are about 10 to the minus 1. We've got roughly 4 orders of magnitude difference. Our x's small approximation is likely to work here, so let's try it. So testing our x is small. Get 1.8 times 10 to the minus 5 equals 1/2 x. So x is equal to 3.6 times 10 to the minus 5. And if we take that and divide it by one of our concentrations, we should see that x is small works. And x is also the concentration of our H+. So we'll do negative log 3.6 times 10 to the minus 5. And we get an answer of 4.44. So not really anything new other than we're starting with some of our products. There is an equation that's helpful for relating the pH of a buffer solution to the initial concentrations of its buffer components. It's the Henderson-Hasselbalch equation. Henderson, an American, no trouble pronouncing that. Hasselbalch, or however you pronounce it, Danish, the L is pronounced apparently and the CH is pronounced like a K, from what I could find. You'll also hear people just say Henderson-Hasselbalch. So, whatever you want is fine, really. So we want to relate the pH to the initial concentrations of the buffer components. You don't need to know how to do this. I think it's kind of cool. We'll see if we can execute it. We know for this equation, why am I starting over here? Wrong button. Good start so far. Ka is our concentration of H+ times the concentration of A- over the concentration of HA. Water being a liquid, we can ignore it. Nothing new with our Ka expression there. We want to get straight to our pH based on these initial concentrations. So we are trying to isolate our concentration of H+, then negative log both sides, since negative log of H+ will give us pH. Fortunately for us, that requires just a little bit of algebra to get started. So to get the concentration of H+ by itself, we're going to move over the HA and the A-, and I'm going to flip it left to right as well. So concentration of H+ equals Ka times HA over concentration of A-. So now we've got our hydronium by itself. And let me draw a longer arrow, and I'll say we're going to negative log both sides. So our left side, negative log of H plus. On the right side, we get negative log Ka HA over A minus. And we'll swoosh all the way back over to the left side. This negative log of H plus turns into pH. So we've got pH like we wanted. And we have a bit of a mess inside of our log on the right side. We can untangle this. So the negative log of Ka we can separate from the HA over A minus thanks to some of our log properties. So we'll get negative log of Ka minus the log of concentration HA over concentration A minus. Is there anything else we can do to make this a little cleaner, make it a little nicer?
Turn the negative log of A minus into POH?
Negative log of A minus doesn't turn into POH. There's a different thing though. There's a different P that we can get in there. And that's going to be our negative log of Ka. Negative log of Ka is pKa. So pH equals pKa. At the same time, we can get rid of the negative in front of this log by flipping the position of the HA and the A minus. So we're going to invert those, and that'll turn that into a positive. So we get pKa plus, why did I change colors? Plus log concentration of A minus over concentration of HA. And that is the Henderson-Hasselbalch equation, which we just get for free on the next slide. Again, you don't need to know that derivation. It's mostly just to show you like where it came from. And so we've got our Henderson-Hasselbalch equation here. That will come in handy, be very helpful. And this is very useful, incredibly useful, as long as the X's small approximation is valid. If the X's small approximation is not valid, then it does not work. Because secretly, right, those are our equilibrium amounts. No, they're not our equilibrium amounts. They would be our equilibrium amounts thinking of how to write this. So we've got our base, that's our A minus. Initial is going to be equal to our amount, final or equilibrium rather, when X is small, because otherwise our thing that we wrote for our equilibrium form, our A minus at equilibrium is the initial concentration, and it's going to be plus X. So So thinking back to our ice table. So if x is not small, then we've got a plus x term that goes along with our a minus. And for our acid, we'll have a minus x term. Those don't get canceled out if x is not small. That also means that we are getting an approximation with the Henderson-Hasselbalch equation. Anytime we want to, though, we can use our ice table approach. Let's calculate the pH of a buffer solution. We're going to do it as an equilibrium problem and using our new Henderson-Hasselbalch equation. We want to find the pH of a buffer solution. We're given initial concentration of hydrogen cyanide, a weak acid, and potassium cyanide, the conjugate base. Our Ka is given to us. So our system is going to be HCN in equilibrium with H plus and Cn minus for the stuff we care about. Our Ka then is concentration H plus, concentration Cn minus over concentration HCN.
Does it matter if we write CN or KCN?
It doesn't really matter if you write KCN or CN. If we had magnesium cyanide that we added instead, then we would need to calculate our concentration of Cn minus. So that's one place where it would be a problem. But since it's a one-to-one thing, it's fine here. And then we get to do an ice table. So we've got HCN, H plus, Cn minus, our initial, our change, our equilibrium. Our initial for HCN, 0.250 molar. Our initial for H plus, roughly 0, not exactly 0, but very close. For Cn minus, 0.170. Since we have basically no H plus, we are going to see a shift left to right. No surprises there, I hope. So we get our usual minus x plus x plus x. Then we get 0.250 minus x, x, and 0.170 plus x for our equilibrium values. So our Ka is equal to x for H plus times 0.170 plus x over 0.250 minus x. And this is where we would normally do the x is small approximation. And we could definitely do x is small here. We've got a Ka of 10 to the minus 10, and our concentrations are upwards of 10 to the minus 1. But we saw with our Henderson-Hasselbalch derivation and like the equation earlier, like when x is small, that works, and it's exactly the same thing. So there's no point in showing you that, I feel like. So we're going to just go ahead and do the full quadratic. You're welcome to just not participate and watch if you want. So we're going to multiply both sides by our 0.250. We're going to get 4.9 times 10 to the minus 10 times 0.250 minus 4.9 times 10 to the minus 10 x equals 0.170 x plus x squared. We'll rearrange that to x squared equals, sorry, not equals, 0 equals x squared plus about 0.170x. It's going to be a little bit higher than that, very, very slightly higher than that, minus, I'll put it into my calculator, 4.9 times 10 to the minus 10 times 0.250. So we've got our A, B, and our C for a quadratic equation. And so I run off to my Pauli solver. .170 plus 4.9 e to the negative 10 and negative 4.9 times 10 to the minus 10 times 0.250. We solve, and our x values, x1 is 7.205882316, 31 times 10 to the negative 10. X2, I'm wondering if I put something in wrong. Negative 0.170 dot dot dot. It's negative, we're not going to be using that one. Oh no, I'm fine here, probably. Okay, so this x1, that's the value that we care about. That's the value for our H plus. So our pH is, store x1 as x, quit, negative log of x1, pH of 9.14. And then we have our Henderson-Hasselbalch approach. So pH is pKa plus log of the concentration of the base over concentration of the acid. We'll do that in purple. Plus log base over concentration of the acid, and those are our initial concentrations that we put in. So 9.31 plus the log of 0.170 over 0.250. Technically both molar, those molars will go away. They're wisdom teeth after all. So 9.31 plus log 0.17 divided by 0.25. And wouldn't you know it, got a value of 9.14. And we'll add some extra digits. So 250 for the blue one, it's 231. So we're only different out in the 10,000ths place. So if we don't care about being precise to the like 100th of a percent, when our x is small, at least this small, we can just use our Henderson-Hasselbalch equation and save ourselves a lot of time and headache. Questions? Good. A buffer contains the generic weak acid HA and its conjugate base A-. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which of the following statements is true? I'll give you a little bit of time to think about it. All right, coming back, we want to be thinking about Henderson, but not just about Henderson, also about Hasselbalch. So pH is the pKa plus the log of concentration of the base over concentration of the acid. We've got values for pKa, 4.82, and our pH of 4.25. And the log part is still there. Move everything else down. So we are looking for a situation in which the log of A- over HA is negative. 4.82 is bigger than 4.25. For these two things to be true, log A- over HA must be negative. When is a log negative? Yeah, a log, I like the chemming on that. Logs are negative between 0 and 1. And logs are positive between 1 and our upper bound infinity. So in order for us to have our log be negative here, our concentration of A- needs to be smaller than our concentration of HA. So A fulfills that condition. And you could plug numbers in if you wanted to. Like we could put 1 for A- and 2 for HA and just see what comes out for log. And let's see what that is. Log 0.5, negative 0.301, dot, dot, dot. So we got a negative number, so that fits with what we were predicting. It's probably even more negative than that. So definitely A- less than HA. We can also calculate pH changes in buffer solutions, building on previous concepts. So remember that a buffer resists change, and though it does resist change, the pH still changes by a little bit. So it still changes, but only by a little bit. And that's the beauty of a buffer system. If we weren't buffered, then we would get a much larger change. So to do these problems, we're going to split it into two parts. We're going to do a stoichiometry part, which is not an ice table. We're not doing an ice table for the stoichiometry part. It's just stoichiometry, plain and simple. No surprises, no twists, no turns. So we're going to change or calculate how the addition of acid or base changes the relative amounts of acid and base. And then we'll calculate the pH based on the new amounts. So we do get to do probably an ice table for that. So no ice, and then later we changed our mind, ice. Typical Starbucks customer. Our example, we've got 1 liter of buffer. We've got 0.100 molar of HA and A minus, and we want to calculate what's the pH after we add a small amount of strong acid. So initially, we have 0.100 mole of A minus, and the reason that we're working with moles here is because we have the same volume. So we're just going to work straight with moles, and our HA is 0.100 moles as well. So those are both our given amounts. And we added in 0.025 moles of our H+. Our H+ that we just added in is going to react with our A-. They're going to get used up at the same ratio. So our H+ and our A- react. They both lose 0.025 moles, and they produce 0.025 moles of HA. So we can calculate our change. We're going to have approximately no H+. We're going to have a little bit of A- and a little bit of HA. So we'll use those new values in our equilibrium step. So depending on our values, we can either do a full equilibrium problem if our x is small does not work, meaning that we get to use a quadratic. So if x is small doesn't work, we use our full equilibrium. Or if x is small works, then we can use our Henderson-Hasselbalch equation. So our initial concentrations from the previous problem are 0.125 of our acid. We used up all of our H+ reacting with our A-. So we've got our new amounts, the ones that we carried in from the last problem. We've got -x plus x plus x, like we've come to expect, know, and hate. And our equilibrium values then are what we expect. We don't have a Ka value, so we don't calculate anything here. But that's just showing how it would work. So we're adding one small step in the front, but we've also learned the Henderson-Hasselbalch equation that can save us a lot of time. So overall, I would say things are getting easier. It's just more steps, more things to remember. So in that way, a little more difficult, but less work for us. If we add a small amount of strong base, it's the opposite. So we would set up our equation in the other direction. So we're adding hydroxide on the left, and that's going to use up some of our HA. So set up stoichiometry. You don't have to do it like in this table. but you want to set up your stoichiometry for adding acid or base. Doing a table could be good. If you don't want to do a table, that's fine too. Just find something that gets you the correct numbers. I don't know why I'm writing balance equation because it's like always going to be 1 to 1, but whatever. So if we add a small amount of strong acid to a buffer, it converts some of our base to acid. It does the expected and decreases the pH. So there's nothing unusual or weird other than we have to account for a little bit of a reaction. If we add a small amount of strong base, then it increases the pH, becomes more basic, more alkaline. It increases the pH. That's also what we expect. So there's no big surprises here. We just need to account for the reaction. Not far, for. So we need to account for that acid-base reaction, and that's the first step of those first 2 steps. So our stoichiometry part, we're doing some acid-base reaction, and then we do our stoichiometry step like we've done with ice tables before or with the new Henderson-Hasselbalch equation. Questions? All right, that'll do it for part 1 of chapter 18.